analysis session. The session will have 3 talks, and the final talks will be a recorded video. So the first talk is Discrete Gaussian Sampling for BKZ Reduced Basis by Amore Puri and Yi-Xin Shen, and the talk will be given by Yi-Xin.
Thank you. So in this talk, I will assume that you all know what a lattice is, and you also know what a Gaussian distribution is. Its a probability mass function is defined by rho s of x here. And so a discrete Gaussian distribution is very similar to the continuous one, but the only difference is that its support is only on a given lattice L. And so the probability mass function in this case for a given vector x will be defined as rho s of x divided by a correction factor, like a normalization factor, which is the Gaussian mass of the lattice L. Here, I give you several pictures of the discrete Gaussian distribution on different lattices. So one important problem is to sample from this discrete Gaussian distribution. Usually we are given as an input a basis of the lattice and also a parameter s, which is the width of the distribution, and we want to sample from this distribution that we call DGS for short. So the complexity of this problem really depends on the parameter s. When s is large, it's usually very easy because the discrete Gaussian is very close to the continuous one. So we can just sample from the continuous Gaussian and then round to the closest lattice vector. And when s is very small, it becomes much more difficult because intuitively, in this case, the probability distribution will be concentrated on the 0 vector and also on the shortest vector. So, so basically, this will help us to solve the shortest vector problem, which is a very difficult problem in lattice-based cryptography. And somewhere in between, there is this smoothing parameter. So I give you the definition here, but you don't really need to understand it. So it's just the threshold that tells you that separates the two worlds, the continuous world and also the discrete world. And indeed, it's already difficult to sample from the discrete Gaussian at the smoothing parameter. So it's not known, for example, if we do the sampling in exponential time, but only sub-exponential space. And if we can do so, then this will be a major breakthrough. And sampling from this distribution for s smaller than the smoothing parameter is very useful because it will allow us to solve all kinds of hard problems, all problems that you can imagine on lattice-based crypto, so learning with error, SVD, and the shortest vector problem, and the BDD problem. What do we know in the literature? So there are a couple of different samplers. The first one is the famous Klein sampler given by the GPV paper. Its time complexity is polynomial, but the parameter s depends actually on the basis b, or more precisely on its Gram-Schmidt orthogonalization b tilde. So the norm of b tilde is just the maximum of norm of its Gram-Schmidt basis vectors. And the s also depends on another factor, so this square root of log n factor. Then a second family of sampler is more powerful. So its complexity is much larger. It's exponential. It takes 2 to the n over 2 time, but it can sample up to s equals exactly the smoothing parameter for a constant epsilon. So epsilon is equal to 1/3 here. And somewhere in between, there's this sampler from Wang and Lin. It can actually sample for arbitrary s. However, of course, the complexity will depend on the basis b and also on the s. And there's a special case for this sampler. So for s equals the norm of b tilde, divided by square root of pi, you can see that the complexity is still exponential. However, for any n that we really care about in real life, it's actually, you can upper bound this exponential by some constant. So you can really compare it to the GPV sampler, and it's actually much better in this case, because S is much smaller. So when we want to do use Gaussian sampler, discrete Gaussian sampler to do cryptanalysis, what can we do? So GPV sampler is not very useful because its width is too large. So we won't be able to obtain short enough vectors. And the second sampler is way too expensive. So we can only do maybe provable attacks. And somehow, what is surprising is that the third sampler is not well known, and it is so far unused. So maybe a reason for that is that the complexity of this sampler is actually quite involved. So this sampler is called Markov chain Monte Carlo based sampler. What it is doing is that we are working on a Markov chain, and whose stationary distribution is the one that the distribution that we want to sample from. So it's the discrete Gaussian distribution here. And so we work on the Markov chain, and in the end, it will converge to its stationary distribution. And the time complexity for this sampler is related to the spectral gap of the Markov chain, and it's so 1 over delta here, which is this expression here. So you can see again that there's no restriction on the parameter S in this sampler. However, the complexity depends heavily on the basis, on the shape of the basis. And it's also hard to estimate because already the factor 1 over rho S of L is the Gaussian mass of the lattice, and it's usually difficult to know what it is. But we can already do something here. If we use the Poisson summation formula, we can already have the first equality here. And then we can upper bound the factor 1 over rho 1 over S of the dual lattice by using the fact that S, by adding a constraint that S should be larger than the smoothing parameter. So by definition of the smoothing parameter, if this is the case, then the first factor can be upper bounded by some constant. So we only need to deal with the product term. And remark that because it's already difficult to sample from the smoothing parameter, so this constraint is not like a huge one. So for the following of in the following of the talk, I will just assume that we are in a regime where S is larger than the smoothing parameter for constant epsilon. So now let's see what we can say about the product term. Which is like a product term of different Gaussian mass for Z, for different parameters S. So let's see what rho S of Z, how rho S of Z behave. For S smaller than 1, it's really close to 1. And then for S larger than 1, this function is actually very close to S. So imagine that we are in the case where the norm of B is larger than S. Then for each term in the product, we can upper bound the norm of B tilde of the norm of Bi tilde by the norm of B tilde, just by definition. And then for each term, we upper bound it by the norm of B tilde divided by S. So, so in total, this product can be upper bounded by this norm of B tilde divided by S to the power of n. So this is quite pessimistic because imagine a situation where a lot of Bi tilde are small. So this upper bound is not at all tight. This is, for example, the case for BKZ reduced basis. So we imagine that we can do much better for this kind of basis. So now what is the BKZ reduced basis? BKZ algorithm is just a lattice-based, famous lattice-based reduction algorithm where there's a parameter beta, which is the block size. So what we do is we try to solve iteratively the shortest vector problem in sublattice, in some sublattice of size beta, and then we update the basis iteratively. And in the end, we get some better reduced basis. The complexity is exponential in beta. And in the end, the basis that we are going to get has a very interesting feature, which is the norm of BI tilde should decrease exponentially quickly. And in the literature, people often use this geometric series assumption that basically describe this phenomenon. So we can, for any I, we can actually write down the norm of BI tilde, which is like an explicit expression, and it's exponential in with respect to I. So this assumption is reasonably accurate for beta large enough. It should be larger than 50, but much smaller than n. Now let's see what it will give us for the MCMC complexity when we assume that the basis is BKZ reduced. Let's look at this product term again. So now we will replace all the BI tilde by its expression given by the GSA assumption. And we also use the fact that rho S of Z should be almost equal to S for S larger than 1. So we, for all these terms in the product, we only keep those i's such that the norm of BI tilde divided by S is larger than 1. And then we put everything together. So very informally, we will get a new complexity estimate, which is much better than the previous one, because you can see that now we have a square root term on the norm of B tilde instead of just the norm of B tilde before. And also, now the exponent is something that depends on the block size beta. So it should be smaller than n. So what I've told you so far are just intuitions. It's not very formal. What did we actually do in the paper? We actually give an upper bound on the product term, so the complexity of the BKZ, the MCMC sampler for the BKZ reduced basis under the GSA assumption. Unfortunately, the formula is quite horrible, so I didn't write it here, but I will explain it later anyway. But the formula is explicit, and one important feature for us is that it's very efficiently computable, meaning that we can compute it in constant time. And then we compared between the complexity of the MC sampler based on the GSA assumption with the complexity of the sampler on actual BKZ reduced basis, just to see whether the GSA assumption is good or not. We also compared the complexity the complexity of with the GSA assumption with the upper bound, so the horrible formula that I didn't show you, to see whether this upper bound is tight. So I will tell you more about these different points in detail now. The first one, so the comparison between BKZ and GSA for MCMC with respect to the actual BKZ reduced basis. So we know that GSA is relatively accurate, but it's not clear how it will affect the MCMC complexity, because now we have a product term of, it's a product of n terms. So what we did is that we sampled different random BKZ reduced bases for a lattice, and then we computed its actual complexity, And we also computed the complexity based on the GSA assumption just to see the difference. So in the graph here, the x-axis is some factor x, which is the scaled volume of the lattice divided by s. As you can see that when x is large, so close to 1, there's some discrepancy. But when x is small, it's actually quite accurate. And what we will use for our application is actually in the regime where x is quite small. So it's actually quite good. But still, you can criticize us that, like, because we are limited by our computation power to generate actual BKZ reduced basis, we can only do this graph for up to dimension n equals 150 and beta equals 70. So we don't know how this will scale for larger dimension n. One way to do so maybe is to use some BKZ simulator and to see what this will give us. So what we will do in the following is just to claim cautiously that maybe for small enough x, this is accurate. Now the second point is so this was the horrible formula that I didn't show you before. So we give this upper bound on the complexity under the GSA assumption. You can see that the upper bound contains two terms. The first term, log of a, is actually the term that I showed you before, the square root of the norm of BTO divided by s to some power which depends on the dimension beta. And then there's a second correction term, which is a sum of p terms for any p odd. So the important thing is that A is the first term is trivial to compute, and it's already a quite good formula for intuitions. And then the other correction terms are very ugly, but also cheap to compute, and they quickly get smaller as L tends to infinity. And in practice, we actually recommend people to use p equals 3. Because it already gives you almost perfect approximation. So we did some experiments about that. Let's see what it gives us. So on the top here, I draw the complexity of the sampler under the GSA assumption for different lattices of different dimensions and also with different block size. And then at the bottom, so I draw this difference between the upper bound and with the actual complexity. For here, I draw for p equals 0. It means that I only draw for the correction term. No, not the correction, the dominant term. So you see that the difference is quite large, especially for n large. But then when we take p equals 1, so only one correction term, then the difference is already smaller. And then when p is equal to 3, the difference is now negligible. So that's why we say that in p equals 3 is enough for computing this upper bound. So now let's see some applications. Why did we do all this? Actually, in our previous paper at Eurocrypt, we described a dual attack on the learning with error problem. It's a provable dual attack, and in which we use the discrete Gaussian sampler as a subroutine to generate short vectors on the dual lattice. And in order to understand the complexity of the attack, we actually need to optimize the choice of several parameters, so beta and s, for example. So we run an estimator for many parameters and then choose the best one. However, estimating the complexity of this MCMC sampler using the product term is very slow because it's like a product of n terms. So instead, what we did was that we used a very crude but fast approximation. But this somehow limited how small the parameters can be chosen. So in this paper, with the new approximation formula, we get actually better, we get less constraints on the parameters, and then this allowed us to unlock better choice of parameter. Let's look at the numbers that we have. So in our Eurocrypt paper, we have actually two regimes for the attack. There's a really provable regime without modulo switching, and so the attack is not very efficient. And then there's also another regime which corresponds to maybe a very optimistic hypothetical attack by imagining that we can do modulo switching in a provable way. And then in this hypothetical attack setting, we actually get competitive attack parameters. So in this paper, we revised these numbers, and then you can see that we got significant improvements on the numbers based on the better formula for the discrete Gaussian sampler. And then in the paper, we also had further improvements by doing a smarter parameter search, but I won't talk about this. Just a reminder, so for the GSA approximation for the that I talked to you about, we as I said before, we need the S to be small, and actually in the dual attacks we only use S smaller than 0.1. So the approximation error by using the GSA assumption can be neglected in this case. Okay, so this is the end of my talk. So here I listed the things that I talked about in this talk, and there are some other results in the paper. We did some analysis of the smoothing parameter of the lattice for random Curie lattice L. So if you are interested in this, you can check our paper later. Thank you very much.
Is there any question? Can you come back to the slide on the complexity of MCMC?
This one? Or?
The first, no. When you present the MCMC and you made this, yeah, so this C, yeah, the one right after.
Mm-hmm.
So what you're actually estimating is an upper bound on C, but is this upper bound tight? How tight is this upper bound?
I mean, here this term corresponds to the, so this term here is actually the first, like the dominant term that we see, sorry, here. So this term. So, and then there's like the correction term.
But no, so let's come back to the first slide. So
Okay.
C is the real complexity.
Yes.
And this product of Gaussian mass is the upper bound. So that's the one you were trying to estimate. But
Yes.
could it be that C is much lower than your upper bound?
Well, there's just, okay, so this complexity came from the previous paper that, so this theorem here. And I think this is quite tight from what I understood from the previous paper. And so there's only one term, so which is this term here, which we upper bounded by a constant by using the definition of the smoothing parameter. So you will have you will lose a constant factor, but
then you show curve with experiments. So do the experiments run the actual MCMC algorithm and measure the running time, or are you just estimating your upper bound? So
yeah, for no, we didn't implement the MCMC algorithm. We just here for this we just used we generated a BKZ reduced basis, and then we used the upper bound to to estimate the complexity for the real MCMC for the real BKZ reduced basis. So we use the real BI tilde in the complexity to estimate it.
So this is just a comparison of upper bounds.
Yes.
Okay.
Mm-hmm.
Okay, thanks for the clarification. Okay, so let's thank the speaker again.